All right, welcome everybody. My name's Dr. Alyssa Griffin, and I'm a postdoctoral researcher at Bodega Marine Laboratory at the University of California, Davis. And today I'm going to be talking about climate change and ocean acidification, which are two different but related problems. So I don't know if you guys like soda, but I love soda. You know, when you open soda, it makes that fizzing sound and there's all these bubbles inside of it. Well, those bubbles are made up of a gas called carbon dioxide, and that's what makes it so fizzy. So carbon dioxide is in our atmosphere, and it's only a tiny percent of our atmosphere. But it helps to keep our climate, so the temperature of our planet, suitable for us to live on it. So it makes it so it's the perfect temperature, kind of like Goldilocks. It's not too cold, it's not too hot, it's just right for all the life forms on the planet, including human beings. When we emit CO2 or carbon dioxide into the atmosphere, it's not necessarily a bad thing. It's a naturally occurring gas that exists in our atmosphere. However, over the last 150 years, even though carbon dioxide is a naturally occurring gas in our atmosphere, we've been sending more carbon dioxide into the atmosphere at an unprecedented rate. So a rate that we've never seen over the history of the entire Earth. And all of that carbon dioxide is coming from the burning of fossil fuels. So things like gas and oil and coal and all these other hydrocarbons that we use to power our cars and to run our electricity and provide power for all the things that we do in our day-to-day lives. And this wouldn't be a problem because, again, carbon dioxide is just this naturally occurring gas. But the rate that we're sending it up into the atmosphere is so unprecedented that we're actually creating a blanket around the Earth of carbon dioxide. And remember that I told you carbon dioxide sort of helps trap this heat. It creates that nice blanket, again, that makes the temperature of the planet just perfect for us. But if we have too much carbon dioxide, it actually starts to make that blanket just a little too thick. So it's like sleeping with a big comforter in the middle of summer. Not good, right? And so that's what's happening to our planet. We're putting more and more carbon dioxide up into the atmosphere, which is making that layer of gas thicker and thicker and thicker. And it's creating this effect called the greenhouse effect. So basically, heat is coming in from the sun. It hits the surface of the Earth and bounces back into the atmosphere and back into space. But then some of it actually gets trapped by our atmosphere by greenhouse gases such as carbon dioxide. So when there's too much carbon dioxide in the atmosphere, it traps way more heat than is usual or that is suitable for us all to live here at a comfortable temperature. So this collective effect is what we call climate change. So the increase of greenhouse emissions from human activities that are creating differences in our global climate, we refer to as climate change. A lot of this carbon dioxide is going into the atmosphere. It's also taken up by plants and other organisms that live on land. But what's interesting is that actually 1/3 of the carbon dioxide that we emit every year is actually absorbed by the ocean. And if you have a hard time sort of thinking about that, gas going into the ocean, think about your soda again. Those bubbles that go into your soda is like the carbon dioxide going into the ocean. And so the ocean is kind of sucking up this gas from the atmosphere. And while that sounds like it wouldn't be a big problem, what happens is that as the ocean takes up that carbon dioxide, the chemistry of the ocean is actually changing. So now humans have not only impacted the chemistry of our atmosphere, but in turn, we've impacted the chemistry of our oceans. So I'm going to talk a little bit more about this process, which is called ocean acidification. And I'm going to show you why it actually is a big problem for the future of marine life. All right, so maybe some of you have seen this before. This is called the pH scale. The pH scale tells us how acidic something is. So if you think of tasting a lemon, ugh, it doesn't taste good because it's so acidic, right? But you also wouldn't want to lick a bar of soap either, right? That's really basic. Basic is what we call the opposite of acidic. So either end of that spectrum, not great. But water, which we drink every day and that we need to survive, is right smack in the middle of that scale. So you can see in this picture here, it's number 7 on a 0 to 14 scale. And so right in the middle, that sweet spot is where, things taste good. They help us regulate our bodies, all things that are good. So the ocean is actually right around here is ocean pH. So the pH of the ocean. So the ocean is about 8.1 on the pH scale. So it falls right around in here. So it's a little bit basic, but not too much different from regular water. And turns out that that's a great place on the pH scale for marine organisms to be living. They feel very comfortable at that slightly basic pH relative to regular water, right? So it's a little more basic than water, but not as basic as something like baking soda or soap or ammonia or the other things that you see on this scale. So what happens when we add carbon dioxide to the ocean is that we're actually moving down the pH scale. We're taking this seawater and we're moving this way and we're making it more acidic. So big deal, it's a little bit more acidic. Seawater is just becoming closer to regular water. Doesn't seem like a problem. Well, I've brought a couple tools here to demonstrate why this is a really big problem. All right, so the first thing I have here, let me tilt my camera, hopefully you can see this, is just a regular glass of water. Okay, I swear I put nothing in it. There's nothing else in here than just regular water from my tap. All right, I'm gonna go ahead and pour some of my soda into another glass. So here's another plain glass. And you can see all those carbon dioxide bubbles in my glass of soda. So we're gonna just have these nice glasses of water here. So again, I have my regular glass of water, no bubbles, and my nice bubbly soda water. All right, so remember that I told you that when we add carbon dioxide into water, it actually makes it more acidic. So knowing that, I would love for you all to make a hypothesis. So a hypothesis is an educated guess about what you think is happening in a system. So if I'm taking my regular water versus my soda water, I want you to take an educated guess about which one you think is more acidic, given that now you know carbon dioxide plus water equals acid. So I'll give you a second to think about it. All right. So now we actually have a way that we can test which of these waters is more acidic. And I'll show you. We have this indicator dye here called phenol red. Okay, and I have a little scale here that shows us that when we're over here on the more red and purple side of the scale, this is more basic or higher pH numbers. And when we're on the left side of the scale, it's more yellow and corrosive or acidic or lower pH numbers. So given that in our little experiment here, the more acidic water should be have more of a yellow color. So let's take a couple drops and see what happens. So, all right. Okay, so here are my 2 glasses of water. Here's my phenol red indicator, and we're just gonna put a couple drops into each cup. And remember, we want to be very controlled with how we do this. So I'm going to put the same number of drops in each cup. So I'm going to put 10 drops in each cup, just so that we know it's not a difference in the dye that we added. All right, so over here, our regular water. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into our soda. And what do you see? You can see that the regular water is much more red, which remember we said was more basic, higher pH over on this side of the scale. Whereas our soda water is really yellow, which is corrosive, acidic, and on this side of the scale. All right, so you may be asking, well, why does this matter? Who cares what the acidity of the ocean is? Well, the things that care are marine calcifiers. So marine calcifiers are organisms that live in the ocean that make their hard parts, their skeletons and their shells and their spines out of calcium carbonate, which is a mineral. And that mineral actually really doesn't like acid. It actually responds to acid by dissolving. So it falls apart, it starts to wear away. You can kind of think of this reaction the same way as adding vinegar to baking soda if you've ever done that fun experiment with a volcano. It's pretty much the same thing, but a little less, a little less intense. So all of these marine calcifiers, calcium carbonate is really important to their survival. And if the ocean continues to become more acidic, that's really going to create issues for them. I'm going to show you a little way that you can think about this. So here, I'm just going to tilt my camera back up. I have Tums. I don't know if you all have ever seen this, but if you ever have a bellyache or your parents have a bellyache, they may take a Tum. And what this does is it actually is just made up of that mineral I told you about, calcium carbonate. I don't know if you can read that, but if you read that label right there, you can see it's calcium carbonate, which is the same exact material I was telling you these marine calcifiers make their shells and their hard parts out of. So knowing that, I want you to imagine that I have a bottle of marine calcifiers here, okay? I have a bottle of shells or a bottle of urchins or any of the other creatures that you see here. And I'm going to take two of my creatures, and I'm going to see what happens when I put those creatures into my different waters. So let's pan down again to our waters. All right, so I have my two marine calcifiers here. All right, you can see exactly the same. I took them out of the same bottle, and I'm going to put them into the cups. Okay, so first one into the regular water. And hopefully you can see not much is happening here. It's just kind of sitting at the bottom, not very exciting. Now let's put this into our acidified water. And hopefully you can see at the bottom of this glass are a ton of bubbles. Here, we have a little condensation on the outside. Can you see all of those bubbles and how quickly this tablet of calcium carbonate is dissolving? All right. So hopefully now, again, if you imagine those as marine calcifiers or things living in the ocean, you can see that if I had a shell made of calcium carbonate, I definitely would want to be living in this water versus this water, right? I can hear it fizzing. I can hear my shell dissolving as we speak. All right, so that's why ocean acidification is a huge problem for marine calcifiers, because as our ocean continues to get more acidic, the more dangerous it becomes for these calcifiers and the harder it is for them to build their shells and their skeletons and all of these hard parts that they need to dissolve. So of all of these marine organisms, there's one in particular that people are particularly concerned about, and that's coral reefs. So coral reefs are so beautiful. You can see from this picture that they're just amazing ecosystems, and they're full of life, and the corals support an abundance of biodiversity and different organisms, and they're often called the rainforests of the ocean. And they're also extremely important to coastal communities that rely on them. So many coastal communities rely on them for food, for recreation, and lots of other important activities that the corals can provide by being there. Unfortunately, corals are not doing so well. So corals are actually made entirely of Tums, if you think about it. They are made entirely of calcium carbonate. So this whole picture that I'm showing you here is just a giant picture of calcium carbonate. So you can imagine that if I was an entire coral reef ecosystem sitting in acidic water, I probably wouldn't be doing so hot. And that's not great because, as I said, corals support a whole bunch of other life too. So if the corals aren't doing well, then all the other organisms that depend on them, including humans, are not going to be doing too well either. The other issue that's happening with coral reefs is that, remember I told you carbon dioxide in our atmosphere is increasing the temperature of the planet. Well, a lot of that heat is actually being taken up by the ocean. And that heat in the ocean is actually also impacting coral reefs. And that's something that we call coral bleaching. So corals actually have tiny little organisms that live inside of them and give them their beautiful color, these vibrant colors that you see here. And when when the temperature gets too high, those little organisms actually will leave the coral, and the coral will lose all of its color and will end up just looking like a white tongue. And so that's why we call it coral bleaching, because it looks like the corals got bleached and they went from being these beautiful colors to turning stark white. And so it's a really sad thing to see, and it's happening all over the world. On the left here, you can see a really healthy coral reef where all of those little organisms are still living inside the corals and thriving and helping the coral support all of these other life forms and support itself. On the right, sadly, you can see this is what a bleached coral system looks like. So you can see that it's lost all of its color, and other organisms have come and grown on top of the corals. And so these corals are really sick. And those are the bleached corals on the right. So one thing that I study is I actually go to these places and I get to study the coral reefs and see how they're responding to these changes in ocean chemistry. So this is a picture of Lizard Island, which is off the Great Barrier Reef in Australia. And the Great Barrier Reef is a huge chain of coral islands and coral reefs like the ones on Lizard Island. And it's really just a beautiful place to be. But again, because of all of these threats to corals, it's really experiencing a lot of trouble. And so the reason we go there to study it is to try to help save these environments and to help protect them from these changes in our planet. So one of the ways that we coral reefs is by going underwater and conducting experiments on scuba. So scuba is a system that we can use to breathe underwater, which I think is so cool. It's like being a mermaid, basically. So I have a little video here to show you some of the experiments we can do underwater. Okay, so here I am with my colleague who you just saw turn the camera around, sampling some of our experiments underwater. So I'm on scuba, I'm breathing, that's that whistling sound that you hear. And we take all these syringes and we can actually take water samples from the bottom of the coral reef, and we can take those samples back up to the surface in order to analyze them in our lab. And the water chemistry can tell us important information about how the reef is doing and the health of the reef. And these chambers that you see here are actually meant to tell us about the sediments on the reef. So coral reefs, these carbonate materials are tums. They can get broken apart and broken down, and all of those sediments end up as the foundation of the reef. And so here what we're actually doing is we're studying the foundation of the reef. And if you think about a coral reef like a house, you would want to make sure that the foundation of your reef isn't dissolving away, right? And so that's why we study the sediments, is we want to make sure that the coral reefs can continue to grow and expand on this foundation, which is the sand or the sediments that you see here. So that's just one of the cool experiments that we can do. And in the chambers, what we can actually do is we can take carbon dioxide gas and we can pump it into the chamber so that it'll actually acidify the water like my soda and tell us how much carbon dioxide is going to impact how quickly the coral reefs start dissolving like my tongue. Systems are really cool. They're really powerful tools that we can use to understand what's going on on the coral reef, in the foundation, in the sand on the reef, and throughout the whole ecosystem in order to in order to understand what's happening on the reef under these changing conditions. These ecosystems are very resilient. They've been around for millions of years. So if we look at the geologic record, we look at how long coral reefs have been around and the other types of extreme events that they've survived, they are strong, resilient survivalists. So I don't want you to leave this being sad or concerned. What I do want you to leave with is to know that the only way that we can really protect and really save our coral reefs is by lowering our carbon dioxide emissions. So we need to make sure that we stay like this water and not like this water. And the only way that we can do that is by lowering our emissions. So we have to save energy, we have to drive our cars less, and we have to hold the people that are emitting those carbon dioxide emissions responsible for their actions. I always like to refer back to the basics, which are the 3 R's: reduce, reuse, and recycle. And if you actually think about those 3 R's, they're in the order of how important or how effective they are, right? So the first thing we can do is reduce our usage of things like disposable items like hand sanitizer bottles or disposable bags. Those are things that we can do first and foremost, is just reduce our usage of things, including things that emit CO2 directly, like driving our cars, using power for electricity, turning the lights off, using nice sunlight instead of direct light. All of those little things can really add up. So that's reducing. Reusing, so for example, the hand sanitizer, what we do in our household is we actually buy a really large bottle, right? So it's just one bottle of plastic, and then we fill our small bottle over and over and over again. And that helps reduce by reusing, right? So we can reuse things. So another example of that would be reusing your grocery bags, right? As you mentioned. So that's another way in which we can decrease it. And then of course, the last one is recycling. And recycling, while it's really important, actually still takes up a lot of energy and a lot of water, which is why I like to say, yes, definitely recycle, but if you can, reduce and reuse first.
Oh, that's perfect. And that's, to me, I think what feeds all of us is if we have power over something, to change it. And I think you've given us some really, really good advice on how we can positively impact our environment. With that, I want to make sure that we end this how we always do. So are you ready with me? We're going to stay curious and
keep on sciencing.